Oceanic and Atmospheric Administration, talking about a three-dimensional finite volume non-hydrostatic icosahedral model.
Yeah, this is our new building, nicely located at the foot of beautiful Flare Island in Boulder, Colorado. Our lab is relative new, just established in early 2000 because the reorganization of NOAA, OAR, Ocean Atmospheric and Research. This is during this reorganization, we have 5 laboratories in Boulder has been consolidated into a super laboratory. So ESIL is almost as big as the rest of the laboratory outside of the Boulder. So it is ESIL a modeling goal to develop a non-hydrostatic global model for weather and intra-seasonal climate prediction. The idea of icosahedral model was introduced by Sandy, our lab director. To reach this non-hydrostatic goal, we decided to take 2 steps. First, we developed a finite volume icosahedral model film, hydrostatic, the target resolution 10 kilometers, and then after the film, we will extend this film to 3-dimensional non-hydrostatic. So I will give you a more explanation of how we do this. So both film and NIM perform finite volume integration on local coordinate. To do this local coordinate, we project the model cell, and then doing this perform the line integration on 2D Cartesian straight line rather than 3D curved line. You can think about this local coordinate as a way to for you to do finite volume line integration along the great circle. So if you do the finite volume integration on the great circle, you may find it useful just to do on the local coordinate. And then the second thing we do is we develop this a multi-step flux corrector transport scheme. This scheme is purpose to primarily is to make sure the layer model don't have a negative layer thickness. The layer model, like a film, is basically running a stack of a shallow water model and couple the vertical flux. In the film, the vertical flux we couple with the rhino black. And once we have these two and then couple with rhino black hybrid sigma theta, then we have a hydrostatic model. We have been running in the last several years film twice a day in a real data medium range weather forecast. What we do is we interpret GFS initial data to film and perform the 7-day forecast at the resolution, 30 kilometer resolution, similar to GFS. So this actually produces a very interesting opportunity for us to compare different numerics, because we use the same initial condition, same terrain, same GFS physical parameterization, running that similar model. And let's see. Let me see. Okay. Go here. So this is show you the 500 minute by ACC over a year, about a year from 2010 to 2009. Below this line is GFS better, above this line is film better. Basically, film has achieved comparable ACC score as a GFS model. And the purpose of this film model is to contribute to UNCEP as an ensemble member of a global model ensemble. So it is UNCEP director and Sandy McDonald's idea that the best forecast coming from ensemble model. For example, this is a good example. In this state, the main drop from GFS does not happen in the film. And then, for example, in some other day, the drop from him does not happen in GFS. So we hope this is film is going to be operational run at the GFS soon as a one member of model ensemble. And for me, I'm really interested in is this opportunity of doing everything the same except the only difference is dynamic core. So this is example of a 5-day preset ball water, which is cloud, is non-smooth field. And this is from GFS spectral model. This is the same, but from finite volume advection. So I personally find this is better than a spectral. And then we also develop an efficient indirect addressing scheme on irregular grid. Working on an icosahedral model is difficult because you don't have left and right. So, so we have developed this efficient indirect scheme. I think MPAS find it useful to do their C coordinate. And then we also look at grid optimization for efficiency and accuracy. For this study, primarily my interest in is to understand what does the spring dynamics do. So this grid is a standard icosahedral bisection scheme. You can see this standard icos grid. The grid line actually is curved discontinuously around that pentagon cell. And the spring dynamics, by attach the spring on each node and then let them push each other until the steady state. It's actually show spring dynamics is reduced this pentagon so that the curve actually can go through pentagon smoothly. But the reduction of this cell actually increase with so-called uniformity, which is the ratio between the largest grid cell and the smallest grid cell. In a standard ICOS grid, it's 1.19, and then with this spring dynamics is 1.4. That means the reduction of time step. Spring dynamics, however, spring dynamics does produce the regularity, which is defined as the H in each cell, the largest and smallest. So the regularity will make the grid smooth. Once we know this, study this geometry, we can actually get this without iteration, without the spring dynamic iteration, and get very similar to the spring dynamic grid. And then we tested this. Basically, if we run, this is David Williamson case file, run without dissipation, you get that noise near the pole because the flow is actually circle. So near the pole, it actually has this strong center. With the spring dynamics and this and the multiplied gray circle, we got a smooth solution without dissipation. So this really shows the effect of grid. Then we ask us a question: what does this impact the real data simulation? So this is the standard icosahedral grid running atom batch was third order with 45 second time step. And this is that improved smooth grid. If we run with the 45 second, it's blow up. So we have to reduce to 36 seconds. But compare these two solutions, you see they actually are quite similar. So there is no justification in the real data to use multiply gray circle. So we use we so-called multiply bilinear. It gives us a 2% increase on time step. It's not a big deal. We also look into a geostrophic adjustment of finite volume A grid in implicit and implicit flow. I think we did this eigenvalue analysis on the A-grid, and we see that the group velocity reverse direction below about 3.5 delta x. But we was wondering, because we have run film several years, seems do not have this A-grid problem. So after that eigenvalue analysis, we did this geostrophic adjustment. We put a perturbation into the center of domain beta plane, running 60 kilometers. The wave will propagate out. So the remnant should be in a geostrophic balance. And so this is indeed this verify. You can see the grid structure coming from the A-grid discretization. So this verify the eigenvalue analysis. But we repeat the same experiment with dissipation, because all of the operational model has a different kind of dissipation. So up with same run with the dissipation. Now this becomes very smooth. So this one may argue that this is geostrophic adjustment with a dissipation. What happened in the A-grid? And I think it's fair at this point. We also not forget, even C-grid has a problem. Okay, now let's talk about NIM. In the NIM, we extend the film 2D finite volume integrate on the line integration into a three-dimensional volume integration. So basically, in each model grid box, let me go to this governing equation. We use the conservative form formulation. If you are familiar with Wolf, this is the Wolf governing equation on z coordinate. So what we do is, in our 3D finite volume, each grid box is treated as a three-dimensional finite volume. And then we integrate with that consistently with U is mass flux. So all of the UVW tracer is affected with the same mass flux through the divergence theory. And the purpose, we hope the 3D finite volume will doing a different integrate the pressure gradient forcing term over topography, different as the traditional theorem following coordinates. So, for example, let me go back to this one. We have this triangle grid in order to sit on the mountain. In order for the control volume to sit on the mountain, we have to make this a triangle grid inside. So this triangle grid allow us to sit on any shape of mountain. But in this horizontal integration, we do this the regular hexagon finite volume integration. The second point I want to point is it's Dr. Lee yesterday, her presentation. Let me draw a similarity between these two. But basically, her orthogonal is actually tilt this 3D finite volume this way, and then go back at the model top, go back. And so for a finite volume, there is no need to have orthogonal grid. The important to recognize that for a finite volume integration, the important thing is the normal vector perpendicular to your model H, to your grid box. So this is just like traditional theorem following is Z defined this way. It's not orthogonal to the topography. And because if you define orthogonal, you have to bring it back. So that's the difference. And in a horizontal, we do horizontal explicit semi-implicit tridiagonal solver for vertical propagating acoustic wave. And the time difference scheme, we use the Runge-Kutta four-stage for time integration. And this Runge-Kutta four-stage, we only do the vertical propagation at the last stage. So this saves us substantial computational time. An important feature of the NIM is use the faster GPU to speed up the calculation. This is over the year. The computation speed over GPU is grow much faster than CPU, and also power problem is much less with GPU. Next, I will show you the tester case. Here, I will show you the 2D tester case in 3D model grid. One bubble, cold bubble, mountain wave, internal gravity wave on the ICOS grid, and then aquaplanet simulation on the 3D ICOS grid. Let me explain first about this 2D grid. I think compared to a cubic sphere, for example, cubic sphere can do this nice one line. But for the finite volume integration, like even cubic sphere or ICOS, you need to have this point. If we do only 1D, we still need this in order to do the flux integration, just like as a 3D. And in this 2D, what our solution is, recognize Fy is 0. So for example, this point will be just interpolation in this point to get this. So we do this 2D this way, and then rotate 90 degrees to do the 2D in the y direction. So this will test the flux in the x direction, and when we rotate, we'll test the flux in the y direction. My experience is, after the 2D test, most of the problem debug. So it's actually very nice way to debug the ICOS code. And here, let me show you quickly about, this is, we verify our tridiagonal solver with the explicit formulation. So this is explicit formulation. You can see in the explicit formulation, the wave is more detailed, but it's also introduced the instability. So I think that the tridiagonal solver actually introduced, as it's supposed to introduce desirable dissipation into a system. And this is just density current after 900 seconds. By the way, this all doing with 3D finite volume integration. In here, no topography. And this one is with topography. I just realized last night when I prepared the slide, this is a shear mountain. And then what I did is I used the clamp 2011 smooth the interface, and then construct the 3D volume after smooth the interface using the clamps methodology. And in this DC MIM, it's used 330 delta x. It's inconvenient. So anyway, in this case, I use 500 meter, and then I expand the A a little bit larger. So I'm still continue working on this 2D, and then doing the 3D. I think I need more study on how the effect of the smooth terrain on the 3D volume integration. And this is internal gravity wave, DC MIM 3.1. We test this phase speed. In this case, let me just pass this through quickly. The phase speed is actually quite close to an analytical one. And my most of effort in the last year is really directed toward the physics. In the last year, we implement GFS physics and GRIMS physics into our system. GRIMS is Yonsei University physics. It's a cafeteria. We can choose and pick different physics. And then here I show you the aquaplanet simulation running on the G5, 32 layer in the vertical. The aquaplanar simulation is provide the upward heat flux in the tropics and then downward heat flux in the high latitude. The difference between this heat flux generate the circulation through the thermal wind relation. So we and then we run 800 days doing the three months average compared with Husky, quite similar. The jet stream about 50 meters per second at the 200 millibar, and then there is an easterly. And this is the perturbation pressure. In the tropical is low pressure, and the upload there is a high pressure push this way. Meridional wind convergence, the vertical velocity, upward motion, downward motion in mid latitude. And I also want to show this mean sea level pressure superimposed by the precipitation. The contour is sea level pressure in the mid latitude too high pressure system, over tropical low pressure system. Color is precipitation. Each frame is 20 days. And then you see this, the storm generated at the tropical, propagate to the mid and high latitude and dissipate. And this wave dispersion, the wave behind catch up with the wave ahead, create this trough. And then the interesting thing is this: even with this very simple aquaplanar simulation with topography, we found something very similar resemblance to the global precipitation system. You can imagine if we have topography here and then the warm SST here, we may get a very similar the precipitation pattern. And this just show you the high the multi-resolution with different physics. So this is my conclusion. I think what I need to do is I want to do more tests on the topography and then prepare the NIM model for real data, running at the film resolution to compare with film as a first step. Thank you. That's my talk.
We have time for a few questions. Anyone has one?
I'll throw one out. You mentioned that you implemented NIM on GPUs.
Yes.
Can you say something about the speed up that you're getting?
Yeah, you know, it depends if you do the socket to socket. Right now, the most advanced CPU is 6. It's one socket, 6 CPU. So that means 24 CPU. And then the GPU socket, we still faster 4 times than CPU socket. So I think there is a gain for the GPU, and especially when we have more tracer, because remember our governing equation is if you have more tracer, the more efficient. So yeah, GPU is something that we hope we can contribute to this community. Yeah.
But are you doing hybrid? Are you doing MPI with the CUDA or OpenCL?
Yeah, it's basically right now like CAP, the commercial, or PGI, the commercial company have NIM dynamic core doing tests in their compiler. So right now this speed up, we have both CUDAs, Henkel CUDAs, and the commercial compiler from CAP. I think it's a French company. Yeah. So we are continuing to work on GPU. Yeah.
Okay, I think we're finished with questions for now. So.
All right.